Hello, everyone, and welcome to the real first section of calculus. This is where we start computing derivatives for a function. So we will start first with the basic formulas and the basic rules. And as we progress section by section, we're going to introduce more rules to compute the derivative. So let's go. So first section, basic formulas and basic rules. So just a little bit of notation before going on. So in a question, if we ask you to compute the derivative of a function, or if we say, hey, we have f of x, compute f prime, or d over dx of f of x, etc. There's a lot of different ways to write the derivative of a function. So just a little bit of notation because I'll be using all of that notation throughout. So I will mix it up because I like to mix things up. So here we go. So suppose we have a function y equal f of x. So if I ask you to compute the derivative, so the derivative here, so the notation could be f prime, so f for the function f, and the prime is for the derivative, or I could say compute the derivative with respect to x of f of x, so d over dx of f of x. Sometimes we can just say this is more like a differential notation, df over dx or dy over dx. All those notations are completely equivalent for asking to compute the derivative of a function. So here we go with the first formula, the one I call formula zero. The reason why it's called formula zero is it's because the function is actually a constant. So if we start with a formula or a function that is a constant function, the derivative of a constant is always going to be zero. In other words, f prime is zero. So, and here I'm not giving you the origin story of those formulas. I'm just telling you what they are, and then we're going to be using them to compute some stuff with them. Like our purpose is to apply these derivatives to various contexts. But if you want here, there's a nice little way to visually understand why f prime is zero when you have a constant function. So here I have in blue the graph of the constant function f of x equal to c. And if you pick a point in the domain and you draw the tangent line, of course, that tangent line is going to be an horizontal line, and the slope of a constant function is zero. And that explains very well why is the derivative of f of x equals c is zero. You have to keep in mind that basically f prime is a slope calculator if your function is linear, and in general, it computes the slope of the tangent line. So just to keep this idea in mind, so formula one, because the answer is going to be one, if you start with the straight line y equal x, or f of x equal x, the derivative of x is 1, or f prime is equal to 1. Again, here, pick any point in the domain. If you draw the tangent line at any point, the tangent line of a line is the line. So they share the same slope. And of course, for f of x equal x, the slope is 1. And this idea can be very well summarized with the following remark. If you start with a linear function, mx plus b, if you compute f prime, well, you're going to get m, because essentially f prime is a slope calculator. So if your function is linear and you have the equation mx plus b, the slope of mx plus b is m, thus f prime is m. The real first formula of this section is really the power rule. So we're not just going to be computing derivatives for a linear function, because that would be simply asking you to find the slope of a line. So we're going to look at more advanced function. And the next step in terms of complexity of functions after linear functions, normally you see quadratic equation, cubic polynomials. So we're talking about power functions, or functions of the form x to the power n. So suppose we start. So the next formula, what I call formula 2, suppose you start with a function f of x equal x to the power n. Then computing the derivative of x to the power n works as follows. So you look at the power. So here the power is n, and that power falls down in front of the function and it becomes the coefficient. So if you have x to the power n, it becomes n times x to the power of n minus 1. So what you do with the power, the new power is the former power minus 1. So you get n minus 1. So you have to subtract by 1 the power. So x to the n is n times x to the n minus 1. So again, just equivalent notation. So f prime, so if you're computing the derivative, f prime, it's n times x to the power n minus 1. So make sure you subtract by 1 the power. And the main difficulty, so remember minus 1, the main difficulty with this formula is just to make sure that you can see what is the power of your function. So make sure you see the right power. Make sure you are dealing with a power function. So know what your n is before you apply the formula that the derivative of xn goes to n times x to the power of n minus 1. And the trickier powers are always if you have 1 over x to the n. So this is basically going over exponent rule. My God. So if you have a formula of the form 1 over x to the power n, that's the same thing as x to the power minus n, or if you have the nth root of x, that's the same thing as x to the power of 1 over n. And if you just have the square root, remember that the power is 1/2. All right, so let's apply this formula. And in terms of basic formula, I think this is the harder one. It's not that hard, but it's the harder one. So first example, let's compute the derivative of x to the power 2. So our basic degree 2 polynomial. So here, what is my power? My power is 2. So when I'm computing the derivative of x squared, the 2 falls up front. So I get 2 times x. And the new power is the former power. So 2 minus 1, which simplifies nicely to 2x to the power 1. If the power is just 1, I'm expecting you to write nothing for the power. So the derivative of x squared is 2x. So next example, so even if you're raising the power, it's not really raising the difficulty. So if you have x to the power 7, and I'm asking you to compute the derivative, well, the 7 falls up front as a coefficient, and then the new power is the former power minus 1, so 7 minus 1, and you're just getting 6. So you get 7x to the power 6. Of course, you don't need to write 7 minus 1. If you see it and you write 7x to the power 6 right away, good for you. You're a genius. Now, the more serious example. So if you look at f of x equal to the square root, so if you see a radical term, the first thing you have to do is get rid of that radical term by seeing the right power for it. So if you have square root of x, the right power for it is x to the power 1/2. So make sure you do your preliminaries before you put the function in the mood for differentiation. So square root of x is x to the power 1/2. This is not computing the derivative. This is just in order to see that the correct power is 1/2. So when I'm computing the derivative, that 1/2 falls up front. So you get 1/2, and then you get times x to the power 1/2 minus 1. So what is 1/2 minus 1? Remember that 1 is 2 over 2. So 1/2, or 1 over 2 minus 2 over 2, this will be minus 1/2. So you're going to get 1/2 x to the power minus 1 over 2. You could leave your answer like this, but in many, many books, you will see that there's no negative power, so they will bring the negative power down. So you're going to get 1 over 2 x to the power 1/2. And because x to the power 1/2 is also known as the square root, you can simplify this just a little bit more, and you get 1 over 2 root of x. Nice. So next example, 1 over x. Again, this is a power formula where the power is minus 1. So 1 over x is the same thing as x to the power minus 1, so that I can clearly see for my next example that my power is minus 1. So I can apply my formula. So here we go. The minus 1 falls up front as a coefficient. The new power is the former power minus 1. And minus 1 is minus 2. Again, you could leave it like this. This is clean enough. But in many books, they're going to bring that negative power down and get 1 over minus 1 over x squared. And that's for D. And again, so here, just be careful. The last few examples, it's just a question of reading the power correctly. So 1 over x7, that's x to the power minus 7. So when I'm computing the derivative, the minus 7 falls up front as a coefficient. And the new power is the former power minus 1. So you get minus 7 minus 1, which is minus 8. So you could just leave your answer like this. That'd be fine. But the answer at the end of your book, it could be minus 7 over x to the power 8. And that's for that one. Hello. Okay, over. Sorry, technical difficulties. And then for the last one, so we have the 7th root. That's 1 over 7, but it's downstairs and it needs to go up. So if I do apply both rules here, this is the same thing as x to the power minus 1 over 7. So again here, for those two examples, I forgot to highlight it, but for E, this is a power function where the power is minus 7. And for F, this is again a power function where the power is minus 1 over 7. And here we go. We apply the rule here. So minus 1 over 7 falls as a coefficient. The new power is the former power minus 1. Remember that minus 1 is also minus 7 over 7. So minus 1 over 7 minus 7 over 7. That will clean into a nice minus 8 over 7. Okay, so and that's as good as it gets really for these questions. So, and really in terms of basic rules of differentiation, that example right here is the toughest example. So for basic differentiation, yes, we're going to do exponential and logarithmic, but this is the tougher rule. All right, that's it for that example. Let's move on into more advanced function, even if the rules are a bit easier. So the last two basic formulas are the following. So formula 3 is about the exponential function ex. So if you start with the function f of x is equal to ex, so remember we've seen e before, we used e before when we were computing compounded interest for an investment where the bank account was giving us our interest continuously. But anyways, that's another story. If you compute the derivative of ex, this is the best formula. You get ex again. So if f of x is ex, then f prime is ex again. So very clean formula. And what about the inverse of ex? So the logarithmic function base e or ln of x. So if f of x is ln of x or ln of x, the derivative of ln of x is 1 over x. So in other words, if f of x is ln of x, then f prime is 1 over x. And there's no examples to really use here. Those are the two formulas, and those are the two formulas for the two functions, and those are the two formulas. So ex goes to ex, and ln x goes to 1 over x. But of course, we're not just going to look at pure terms, pure power terms, or ex alone, or ln of x alone. What about 5x7 plus ln of x? So what happens if you're combining those functions algebraically? So the next two rules are the first basic rules of differentiation. What happens when you multiply a function by a coefficient, and what happens if you add or subtract two functions? So here's the set of the first two rules of differentiation, what we call the basic rules. So suppose we have two functions f of x and g of x, and suppose c is a real number, and suppose f of x, we have a derivative for it, and it's f prime, and g of x, we also have its derivative, and it's g prime. What happens, so the first rule, what happens if you compute the derivative of a multiple of that function, so c times f of x? Well, if you know the derivative of f of x, and you know if it's f prime, then just keep the c up front, and that's your derivative. So if you have a coefficient in front of function and you need to compute the derivative of that formula, just keep the coefficient and focus on the f part only. And then the second basic rule, what happens if you add or subtract two functions? So what's the derivative of f of x plus or minus g of x? Well, the derivative of a sum is the sum of the derivatives. So the derivative of f of x plus g of x is f prime plus g prime, or the derivative of f of x minus g of x is f prime minus g prime. So you can really do differentiation term by term, algebraically speaking. And those are your two basic rules of differentiation. All right, times for some examples. All right, let's compute f prime for the following function. So for a, we have 7x squared minus 3x plus 2. So we can see here first that the power of 7x squared is 2. So I'm going to just label, not label, but highlight it. So I have a power function. And I also have a linear function here, minus 3x plus 2. So the way I'm going to do this is, well, the 7, I'm keeping it up front, so I get 7. The derivative of x squared, well, the 2 falls up front. The new power is 2 minus 1. You could write 1 right away or write nothing. And then what about minus 3x plus 2? Well, this is the linear function part. The derivative of minus 3x is minus 3 and the plus 2. Okay, you're left with minus 3. And when you clean this up, 7 times 2, that's a 14. X to the power 2 minus 1, which is x to the power 1. I'll keep it as simply an x. And you get minus 3. And that's it for that first one. So again, so the next one, I see my first power is 7. Then I have a 2. I have then a linear part, minus 2x plus 1. So here we go. So for the first one, so I'm keeping the 2 up front. This is just a coefficient. So you get 7 times x to the power 7 minus 1. Again, if you're comfortable in your skin here and you write already or directly 7x to the power 6, you're a genius. Okay, so minus 7. So x squared goes to 2x. So here I'll just do it. And minus 2x plus 1, the slope of minus 2x is minus 2. Plus 1, and then you can clean this up very nicely. 2 times 7, that's 14, x to the power 6, minus another 14 times x minus 2. Now for C, C is the first real question here. So I did the algebraic preliminaries. So the square root of x, that's x to the power 1/2, and the cubic root of x, that's x to the power 1/3. My 4 is a coefficient in front of the square root, and my 6 is also a coefficient in front of the cubic root. I just keep them right up front of everything. So you get 4. For the first one, I keep the 4 in. So 1/2 falls up front as a coefficient. So 1/2 falls up front. So 1/2 falls up front. The new power is 1/2 minus 1. And then minus 6, you keep the minus 6. This is just a coefficient. And then the 1/3 falls up front. The new power is 1/3 minus 1. Now let's just clean the power. So here and the coefficient, so 4 times 1/2, that's a clean 2. 1/2 minus 1, that's minus 1/2. And then 6 times 1/3, that's another 2. So you get minus 2, and then x to the power 1/3 minus 1. Remember, minus 1 is 3 over 3. So 1 over 3 minus 3 over 3, that's x to the power minus 2 over 3. Now to the next one. And I think C and D here are the tougher questions. So for D, I have x, 2 over x, which is the same thing as 2 times x to the power minus 1. Remember, this is the tougher part of the question, just labeling the coefficient, the powers, correctly. And then 3 over x cubed, that's the same thing as 3 times x to the power minus 3. So let's go. So let's compute some derivatives here. So I keep the 2 up front. So the minus 1 falls as a coefficient. The new power is minus 1 minus 1. And then I have minus 3. Now the minus 3 falls up front as a coefficient. And you get minus 3 minus 1. Again here, if you can write minus 4 right away, you're a genius. Okay, so you get minus 2, x to the power minus 2. And then minus 3 times minus 3, that's plus 9. X to the power minus 3 minus 1, which is minus 4. And here I'm keeping negative powers, I don't care, but maybe at the back of the book, maybe the answer is minus 2 over x squared plus 9 over x4. All is good. And honestly, C and D are, to me, the tougher questions, because when you look at the other two questions, what do we have here? Well, we have 4 times EX, so the formula to differentiate is EX, and I know EX goes to EX, and then the second term is ln of X, and I know ln of X goes to 1 over X. So when you're computing the derivatives, you get 4 times the derivative of EX, which is just EX again. So you're just keeping the coefficient here, the 4, and then ln of X turns into a 1 over X minus 2 babayla. If you clean this up with no brackets, you get 4EX minus 3 over X, and that's your derivative. Is as you can see, as you should feel it, those are easier than power rules, anyways, at least to me. So last example, I have a power function where the n is 9. I have my EX that will turn into EX, and ln of X that will turn into 1 over X, and bye-bye for the constant. So when I'm computing f prime, so I'm keeping the coefficients, you get 2, 9 is falling up front. The new power is the former power minus 1, so let's do it as if we're geniuses now. So this will just give you an x8. The EX will stay EX when you differentiate. The ln of X will become 1 over X. The plus 1 babayla. If you clean this up a little bit, you're going to get 18x to the power 8 minus 3EX plus 2 over X. And those are very nice examples of application of basic formulas and basic rules of differentiation. So for that section on basic formulas and basic rules, which are very, very important to master before moving on into more complex rules, like product rule is coming up, and quotient rule and chain rule, that's it. That's all. Bye-bye.